Okay, we're going to look at some examples of how we use the mole to translate between the world of atoms and the macroscopic world, the one that we can see and observe. Specifically, we're going to be using molar mass and the number of particles in a mole to go kind of between moles, where moles is kind of our sort of our pit stop in between those two, or it's our translator between the two. So I have a world of atoms, I have a world of grams. In order to get between those two, the mole connects those. A mole of any element, whether it's carbon or aluminum or zinc or hydrogen, 1 mole is 6.02 times 10 to the 23rd particles of that stuff. For pure elements, we're talking about atoms. If we're talking about like a compound or a molecule, works the same way. So particles can mean single atoms. They can mean groups of atoms. We call molecules when they're covalently bonded. You could call it a formula unit, which is a group of atoms for an ionic compound. All means the same thing. It's all a particle. It's a group of atoms that have a given chemical formula. Okay. That mole is also the mass that's given right on the periodic table, but in grams. So we use the molar mass in grams per mole to describe how many grams there are of something in 1 mole of something. So, for instance, carbon has 12.01 grams per mole of carbon. Okay, and 6.02 times 10 to the 23rd particles of carbon, you have 12.01 grams of carbon, and we call that 1 mole for short. So let's look at some practice problems using this concept, the chemist's dozen, the mole. All right, a pencil has roughly 1.7 grams of graphite lead, which is just actually pure carbon in it. How many moles of carbon are in your pencil lead? Okay, well, I might not know exactly how to approach this problem at first, but in the end, if we just look at what it's asking for, we're starting with grams. It's asking for moles. Grams and moles are two different units, but they are connected to each other. In the past, how we've converted from one unit to another that has a connection between them is a unit conversion. And we're going to do something like that for this one too. The only difference is in this case, we're using a conversion factor that's a little less familiar to us. So let's set up what we know and see where it takes us. So we're starting with 1.7 grams of carbon. Okay. I know in order to get my answer, I have to get rid of this grams unit. I can't stay there forever. So I'm going to have to divide off of this grams unit and multiply by whatever unit I want, which is, in this case, moles. Instead of showing those two separately as dividing and then multiplying, we usually show this as a fraction bar, something like this. Let me get rid of these so they're not in the way. We show it as a fraction bar, where our old unit that we're trying to get rid of is on bottom, and it will get divided so it gets canceled, like grams of carbon down here. Okay, whatever we're trying to get to is going to go on top, like, for instance, moles of carbon is what we're looking for. So when we multiply that unit, it's going to be tacked on. So whatever's up on top of the fraction bar will get multiplied, and whatever's on bottom will get divided. All right, so now all I have to do is figure out how many grams of carbon are in a mole of carbon. So this is a conversion factor. Okay, just like 12 inches in 1 foot or 60 seconds in 1 minute, I want to know how many grams are in 1 mole. Well, that's what the molar mass is for on the periodic table. If I go and find carbon, it has a number down at the bottom that says 12.01. That means that carbon has 12.01 grams of carbon in every mole of carbon. So let's set that up. In 1 mole of carbon, we have a mass of 12.01 grams of carbon. So if I take 1.7 times 1 divided by 12.01, I should get my answer. It should come out to be about 0.142-ish. Okay, and depending on how you round that, you might get something a little bit different, but I can usually look at your math and say, okay, yeah, you're on the right track, you're in the ballpark, things like that. So you don't have exactly the same way that you chop off the answer. I can still tell whether you got the right answer or not. Okay, our unit is now moles, and actually I'm going to do this in purple since we just converted to moles. So we have 0.142 moles of carbon. All right, and that's our answer. Okay, so really our unit conversion is no different than the way we've done it before. The only difference is this conversion factor is kind of new to us, but it works the same way as any other conversion factor. So let's try some more examples. How many atoms, aka particles, of carbon are in your pencil lead? Well, what relationship do I have with particles that I can use to figure this out? Well, I know that there are 6.02 times 10 to the 23rd particles of carbon in 1 mole of carbon. So if I have moles of carbon down here, I should be able to figure out how many particles that is. If I had exactly 1 mole, that would be 6.02 times 10 to the 23rd atoms of carbon, or particles of carbon. But since I don't, I have less than a mole. I should get less than 6.02 times 10 to the 23rd particles in my answer. To figure out exactly how much, we use a conversion factor and we convert the units. So let's do it. 0.142 moles of carbon. I've got to get rid of my moles unit, so I'm going to multiply by a fraction bar, where my moles unit is going to be on the bottom. Okay, on the top, the unit I want is particles. So I'm going to put particles on the top, and actually my fraction bar is going to need to be bigger. Particles. Let's stretch this out a little bit. Particles of carbon. Okay, which means I've got a conversion factor. Let's do this one in blue. Conversion factor. All right, and in 1 mole of carbon, there are 6.02 times 10 to the 23rd particles of carbon. Okay, just like before, if I multiply by the top, divide by the bottom, I should get my answer. This 6.02 times 10 to the 23rd can be a little bit tricky to put in your calculator, especially if it doesn't just write the math like you would. Sometimes you have to kind of work backwards, or there's like a little capitalized E that means times 10 to the, and that kind of thing. So if you're not sure how to get this to work in your calculator, let me know and I can help you out. But either way, we're going to take 0.142 times 6.02 times 10 to the 23rd divided by 1. All right, and we should get 8.55-ish. 8.55-ish times 10 to the 22nd particles, or atoms, of carbon. And that's our answer. Okay, and again, it's okay if your number is a little bit different. Like when I calculated this before, like last year, I have on my answer key that it was 8.52 times 10 to the 22nd. I'm still going to be able to look at that and be like, okay, yeah, the math was right. You came out to the right answer. If something actually went wrong in your math, your answer would be much different than that. So I'm pretty good at eyeballing and saying, okay, yeah, it's just rounding. You got it. Okay, let's look at some other examples. Okay, a carpenter uses nails that are each made of 1.4 grams of iron. So Our first part is asking how many moles of iron are in each nail. Well, we just did a conversion kind of like this for carbon, where we're changing from grams to moles of something. So let's do it. We're starting with 1.4 grams, so we have really nothing else to work on, so might as well start with that. 1.4 grams. See, iron is Fe, so I'm going to do Fe like that, times a fraction bar. Cool. All right. That means I want to get rid of grams on the bottom. So on the bottom of the fraction bar, I'm going to put grams of Fe, so that unit will cancel when I divide it. Okay, trying to get to moles, so moles is going to go on top, moles of Fe. Let's see, okay. Well, this is another conversion factor. This is asking how many grams of iron are there in a mole of iron? And again, this is a job for the molar mass. So we go and find iron on the periodic table, Fe, and it has a molar mass of 55.85. In other words, in 1 mole of iron, there are 55.85 grams of iron, just like how in 1 foot there are 12 inches. So, in doing this, we should be able to get our old units to cancel. Our grams are going away, and I guess I should have let me cancel these other ones out so it kind of stays consistent. We canceled those. Bam, bam, cancel those. Okay, so what we come out with is going to be 1.4 times 1 divided by 55.85. So let's plug it into a calculator. 1.4 times 1 divided by 55.85. We get 0.0251-ish. 0.0251, something in that ballpark, moles of iron, of Fe. All right. The next question is, how many atoms, aka particles, of iron are in each nail? Oh, again, we just did something like this, but we did it for iron instead. I mean, we did it for carbon instead. Now we're doing it for iron. So let's take what we had before, our number of moles, and convert that into particles. Since we know the relationship between moles and particles, let's take this down here, just like we did for this one. Kind of went through the question there. Okay, 0. Kind of looks like a 6. Let's try that again. 0.0. Man, my zeros are not doing too well today. 0.251 moles of iron. It's going to get converted. We're getting rid of moles of iron. So moles Fe is going on the bottom. Okay. Particles of Fe is going on the top. All right. So again, the question is, how many particles are in 1 mole of iron? Now, the wonderful thing about the mole is it doesn't matter whether we're dealing with iron or carbon or water molecules or formula units of NaCl. In 1 mole of whatever, there are 6.02 times 10 to the 23rd things. So in 1 mole of iron, there are 6.02 times 10 to the 23rd. That big old nasty number. Okay, so if we multiply by the top, divide by the bottom, our moles units should cancel. We'll be left with the unit of particles of iron. So we'll plug this in our calculator. 0.0251 times 6.02 times 10 to the 23rd. We get 1.511-ish. 1.511-ish times 10 to the 22nd. Okay, our unit is now atoms or particles of iron. There we go. Okay, let's look at this next one. Our recipe calls for 0.4 moles of table salt, aka sodium chloride. Well, if your cookbook is giving you moles for your measurements, you should probably just get a better cookbook or look something up online to get a different recipe. But let's work with it. Okay, what is the chemical formula for sodium chloride? Okay, well, sodium, right off the periodic table, is Na. And as an ion, it should have a +1 charge. Let's do this one right here. Chlorine is Cl, and as an ion, it should have a -1 charge. So if I put together Na plus and Cl minus, I just need one ion of each to get those charges to cancel. +1 and -1 cancel out. That just makes a neutral ionic compound, which is good. It's a good sign that we've got the right compound. Okay, so our formula is just going to be, let's do it in green. I haven't done green in a while. NaCl. Okay, what is the molar mass of sodium chloride? Well, the molar mass of a single element is just what the periodic table says for it. So if we just have two atoms of two different elements here, we just need to add up the molar masses of those two things. So I'm going to need to add up the molar mass of 1 sodium plus 1 chlorine. If I had multiple of each, I'd have to do times multiples of each instead of times 1. So let's see. I go find sodium on the periodic table, and it has a molar mass of about 22.99. Our chlorine has a molar mass of about 35.45-ish. Okay, so if I put that all together, 1 times 22.99 is just 22.99. 1 times 35.45 is just 35.45. So I take 22.99 plus 35.45, and I get 58.44. Well, molar mass has a unit of grams per mole, G/mol. Okay, so in a mole of sodium chloride, NaCl, there are 58.44 grams of sodium chloride. So next, we're going to figure out how many grams of sodium chloride are needed in this recipe. Well, we don't have exactly 1 mole, or else it would be 58.44 grams. We have less than half of a mole. So in order to figure out exactly how many grams we need, we're going to calculate, we're going to convert our number of moles. So this time we are starting with moles. 0.4 moles of NaCl times, got a fraction bar. We're trying to get rid of moles this time, so moles is going to go on the bottom. Moles of NaCl is down here. All right, on top, we're going to have grams of NaCl. Okay, so this conversion factor then is going to be how many grams of NaCl are in 1 mole of NaCl. All right, so in 1 mole of something, in this case sodium chloride, I have 58.44 grams of sodium chloride. 58.44. My moles units should cancel out, and I should be left with grams of NaCl instead. So I take 0.4 0.4 times 58.44 divided by 1. The divided by 1 doesn't really do anything to your answer, but sometimes it makes me feel better to do it just to make sure I've hit all the stuff in the fraction bars. So it's up to you. If you feel comfortable with skipping it, that's fine. Again, it won't change your answer. But our answer here, either way, comes out to be about 23.376. Now this is grams of NaCl. So your recipe needs 23.376 grams of NaCl. Let's circle that. Oh, I didn't circle the molar mass before, so let's do that one too. Do a little arrow, point down to there. All right. Let's look at the next one. I think this is the last part in this question. All right. How many formula units, aka particles, of sodium chloride are needed for this recipe? So I just got grams, but if I wanted to change from grams to particles, that would take 2 steps. I'd have to go back from grams to moles, which I should just get 0.4 again, and then go from moles to particles, since I know the relationship between moles and particles. So instead of doing all that, I should probably just start back with the number of moles that I had. We're already given 0.4 moles, and so we started with here. So why don't we just go and calculate for moles to get the particles? So 0.4 moles of NaCl is what we're starting with, but in this case, we're going to go to particles instead of grams. Okay, the old unit I want to get rid of is moles of NaCl. All right. And this time I'm trying to change it into particles. So I'm going to put particles of NaCl on top. All right. There are 6.02 times 10 to the 23rd particles of NaCl in 1 mole of NaCl particles and 1 mole of NaCl formula units. So when I multiply by the top, divide by the bottom, I should get my moles units to cancel out. 0.4 times 6.02 times 10 to the 23rd gets me about 0. Oops, sorry. That should be 2.408 ish times 10 to the 23rd. That should be particles now. Specifically of NaCl. Ooh, that was a bad circling job. Let me see if I can just kind of scooch it. Okay, that's a little better. All right. A grill's gas tank contains 0.0358 kilograms of propane, and we have our formula for propane there, C3H8. Okay, so first they were asked, what is the molar mass of propane? So I've got to add up the mass of 3 carbons and 8 hydrogens. So 3 times the molar mass of carbon plus 8 times the molar mass of hydrogen. Oops, I jumped to the gun. Wrote that. Molar mass did already. H. Okay, it's going to be our molar mass, so now I'm going to fill in the molar masses. The molar mass of carbon is 12.01 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. So if we add this all up, 3 times 12.01 is 36.03. 8 times 1.01 is 8.08. So take 36.03 plus 8.08. We get 44.11 grams per mole. Circle that. Okay, how many moles of propane, C3H8, are in the tank? Okay, well, we have kilograms to start with, but my molar mass is in grams per mole. So I kind of need to be careful about this. I can't leave this 0.0358 kilograms as kilograms, or else it's not going to cancel correctly. I need to change it to grams. Okay, you may remember that if we're changing just the prefix of a unit, all we have to do is move the decimal place. We don't actually have to do any math. So kilo is a prefix that is 1,000 times bigger than grams. Or in other words, a kilogram is 1,000 times heavier than a gram. In other words, in order to put this back to grams, we would need 1,000 grams for every kilogram. Okay, again, you don't have to do math to do this. Since this is all by a factor of 10, we just have to move our decimal point by how many zeros are in our kind of related factor. So if there are 1,000 grams in 1 kilogram, okay, or if you remember there's a chart like KHDA unit DCM for kilo, hecto, deca, base unit, deci, centi, milli. We're going to move 3 spaces, and to go from kilo to regular grams, we're just going to go 3 spots to the right. So we should land at 35.8 grams of C3H8. Okay, now we can do our conversion. So multiply by a fraction bar. I'm trying to get rid of grams of C3H8 on the bottom. I'm trying to get to moles on the top. All right. So now the question is, how many grams are in 1 mole of C3H8? Well, hey, that's what we just figured out with the molar mass. There are 44.11 grams of C3H8 in 1 mole of C3H8. It has a molar mass of 44.11 grams per mole. Okay, so that's good. Got that. Now I have to just do the math. So when I multiply by the top, divide by the bottom, my grams units should go away. 35.8 times 1 divided by 44.11 should get me about 0.812-ish. 0.812 or something in there moles of C3H8. Okay. Now, something that can help you out. Sometimes, even if we get the right units in the right places, like, old unit has to go on bottom, I put grams on bottom, new unit has to go on top, moles goes on top. The numbers that we put in those spots can sometimes get switched up. Like we'd put the 44.11 on top instead of the 1 on top, and the 1 ends up going on the bottom with the grams. So if you get mixed up and you're not sure what number to put where, here is my tip for you. If I can get my pen to start working again. There we go. B1 with moles. You see moles in a fraction bar, you take a deep breath, and you become 1 with moles. In other words, if you see moles in a fraction bar, you put a 1 there. Put a 1 there. Be 1 with moles. So put a 1 with moles. All right. It's kind of goofy, but it helps. It sticks. And we'll probably see it in this next problem. How many molecules, aka particles, of propane, C3H8, are in the tank? Well, we can figure out particles from moles, so let's do that. So we're going to take our 0.812 moles of C3H8, multiply it by a fraction bar, where I'm getting rid of moles on the bottom. Moles of C3H8 is going on the bottom. I'm trying to get to particles on the top. Oops. Particles of C3H8. Okay, and before I even have to start thinking about it, I have moles in a fraction bar, which means what? I'm going to be 1 with moles. So I put a 1 down there. So that's already taken care of. That's good. Now I just have to ask myself, how many particles are there in 1 mole of this stuff? Well, that's where that big nasty number comes in. That's 6.02 times 10 to the 23rd particles. Okay, so I take 8.12 times 6.02 times 10 to the 23rd divided by 1. My moles units are going to get canceled out. I'm left with a unit of particles of C3H8, and I've just got to multiply it out. So 0.812 times 6.02 times 10 to the 23rd gets me 4.89-ish. 4.89 times 10 to the 23rd particles of C3H8. And there's my answer. Okay, so when you see moles in a fraction bar, be 1 with moles. I promise it will help. Okay, let's do one more set of examples. A seashell contains 2.00 times 10 to the 23rd particles of calcium carbonate. Okay. What is the chemical formula for calcium carbonate? Well, let's see. Well, the calcium part is going to be the element calcium, so let's put that there. All right. On the periodic table, let's do it in pink. Keep consistent with what I did before. On the periodic table, calcium has a charge of positive 2. So put a little 2 plus up there. Okay. Now, carbonate is not just carbon as an ion. It's carbon loaded with a bunch of oxygens. It's a polyatomic ion. Specifically, this polyatomic ion is carbon with 3 oxygens, and altogether has a charge of negative 2. A positive 2 charge and a negative 2 charge should come together to cancel just as they are. So the formula for this is just going to be CaCO3. I take 1 calcium ion and 1 carbonate polyatomic ion because this whole thing has a negative 2 charge. Okay, and this is a good sign to show that you really got to know your polyatomic ions, or at least when you're doing assignments and homework, have something close by that can tell you and help you. Okay, the more you use them, the more you practice with them, the easier they're going to be to remember. Okay, so I'm not putting them on here to be mean. I'm putting them on here so that you can help to kind of remember them. Okay, so our formula is CaCO3 for calcium carbonate. We've got to figure out the molar mass next, which means we're adding up the mass of a Ca and a C and 3 O's. So 1 times the molar mass of calcium plus 1 times the molar mass of our carbon plus 3 times the molar mass of our oxygen should get us the molar mass of this compound. If we go to the periodic table, calcium is 40.08 grams per mole. Carbon is 12.01 grams per mole. And oxygen is 16.00 grams per mole. So I add those up. 40.08 plus 12.01. Okay, and then I've got 3 times 16. So let's see. 3 times 16, that's 48. So My 40.08 plus 12.01 was 52.09. And then I'm going to add to it 48, and I get 100.09 grams per mole for calcium carbonate. Okay. Our next part is how many moles of calcium carbonate are in this seashell? Well, we have particles. We have a relationship between particles and moles, so we're probably going to use that. So let's start with what we know. We have 2.00 times 10 to the 23rd particles of calcium carbonate. 2.00 times 10 to the 23rd particles of CaCO3. I'm going to multiply by a fraction bar where I can get rid of particles of calcium carbonate by putting it on bottom. Particles of CaCO3. All right. On the top, I'm trying to get to moles of calcium carbonate. Moles CaCO3. All right. And hey, I've got moles in a fraction bar, so what do? I'm going to be a 1 with moles. So I put a 1 up there, and I don't have to worry about that part. And now I just have to ask myself, how many particles of this stuff are going to be in 1 mole of this stuff? Well, if I had 1 mole of this, it should be 6.02 times 10 to the 23rd. That's how many particles are in a mole of anything. Okay, my particles units should cancel out. So I just have to go and plug this into my calculator. 2.00 times 10 to the, times 10 to the 23rd divided by, I guess times 1 if you want to do the times 1, divided by 6.02 times 10 to the 23rd. And my calculator spits out an answer that looks like this. Now let's do it in a different color. Let's do it in this kind of dark blue. 3.32 times 10 to the 45th, which really seems wrong. Like we've got some big numbers with this here, but not this big. This is nutty. Not to mention, this is supposed to be moles of calcium carbonate. That should be a nice reasonable number. That's why we use moles, so we can take a large amount of particles and make it into a reasonable quantity. This got worse, so something has gone wrong in our math, okay? But I'm pretty sure I plugged all this into my calculator correctly. Your calculator will sometimes try to outsmart you, okay? Because it plays by a lot of rules, including order of operations and how you kind of line stuff up in your calculator and things like that. So in your calculator, let's do pink this time. When you type in 2.00 times 10 to the 29 and do all this, this is what it's going to say. It's going to say, okay, you want me to do 2.00 times 10 to the 23rd. You want me to multiply by 1, which is fine so far. We divide by 6.02, again, good. And that's like, okay, well then after that you want me to multiply by 10 to the 23rd. And we're like, no, calculator, we want you to divide by this whole thing, this one number. But the calculator doesn't know that. It sees this multiplication sign. It's like, oh, okay, so you divide by this and multiply by this. No, that's not what we're really going for. So in order to help yourself from that happening, we have to put parentheses around this whole thing. This whole 10 to the 23rd thing. So that way our calculator will divide by, parentheses, 6.02 times 10 to the 23rd, end parentheses, that whole number. It'll divide by 6.02 times 10 to the 23rd, not divide by 6.02 and then multiply by 10 to the 23rd. Okay, so be careful of that. Use parentheses. Okay, if you're not sure about when to use parentheses, and when it's going to hurt your calculator, stuff like that, you can just put the parentheses around the whole 6.02 times 10 to the 23rd anyway. It'll never hurt anything. You don't need it for multiplying, but you absolutely need it for dividing. So if you want to play it safe, just always wrap up your 6.02 times 10 to the 23rd in parentheses. So that way the whole thing is dealt with as one thing. Okay, now let's try this again. 2.00 times 10 to the 23rd times 1. I'm going to divide by parentheses 6.02 times 10 to the 23rd. I'm going to close my parentheses. And then I put my enter in. Hey, that much better. So it's 0.332-ish moles of CaCO3. That's a lot better. All right, so do not forget those parentheses when you're dividing by your 6.02 big nasty number. Okay, one more question. How many grams of calcium carbonate are in this seashell? All right, well, I can go from moles to grams, so while we've got this moles, we might as well use it. So let's take this down here. We'll use it for our last calculation. 0.332 moles of CaCO3 are going to get converted. I'm going to multiply by a fraction bar. Okay, where I'm getting rid of moles on the bottom. Moles of CaCO3. And I don't even need to know what's going to be on the other side. I see moles in a fraction bar. I'm going to be 1 with moles. Okay. I'm trying to figure out grams of calcium carbonate. So grams of CaCO3 is going on the top. Okay. So how many grams of CaCO3 are in 1 mole of CaCO3? Well, hey, that's what my molar mass is for up here. There are 100.09 grams of CaCO3 in 1 mole of CaCO3. Okay, so 100.09 grams of CaCO3 is going on top. My moles units should cancel. I just have to take 0.332 times 100.09 divided by 1. 332 times 100.09. And we get 33.23-ish. 33.23. And now we're in grams of calcium carbonate. Okay, and this last problem is a good example of why you have to know how to get your formulas. Okay, you got to be able to know your polyatomic ions and how to cancel out your charges to get something happy, or how to read your prefixes and recognize that as how many atoms there are. Because if you don't have the right formula, we're not going to get the right molar mass. If we don't have the right molar mass, we're not going to get the right number of grams, or we're not going to be able to convert out of grams correctly. So again, it's another skill that I'm not making you do because I'm trying to be mean to you or something, or torture you guys. It's because it's going to show up, and it can make a big difference in how your problem works out and what your answer is. So I'm trying to save you points later on, and I'm trying to get you to practice it now. Okay, I promise it will help you. So hopefully these things are starting to come together. Okay, and again, this is no different than the unit conversion we've done before. The only thing that might seem a little different is we're using conversion factors that we're not familiar with. Oh, and don't forget to be 1 with moles, and don't forget to use parentheses around your big nasty number, your 6.02 times 10 to the 23rd.